Okay, part 3 of chapter 1. Guys, this chapter I'm spending a little bit more time on, and so there's a lot more video, simply because I find that most students have problems with this. If we can get past this, the rest of this is going to be pretty easy. I think it's going to be pretty easy. You may disagree. So last time we got barely this far. Okay, so let's now look at some examples, okay? And this is kind of the wording that you might see. And there's a couple of reasons I want to talk about this is really good for us to go over because there are two different approaches we're going to take. And we've talked a little bit about this, but I do want to make sure that we've got the right approach. So remember when I said I want to convert decimal to 16-bit 2's complement. Here's the rule. When it's positive and I'm converting, I'm merely going to convert this using expansion to, so I'm going to just convert this decimal to hexadecimal is what I'm going to use in my case to do this. I want to make sure at the end that I've got the right size, okay? So let's do this using repeated division by 16. 176, 16 goes into that once with 1 left over. 16 goes into 16 once with 0 left over. 16 goes into 11 0 times with B left over. When you do this, guys, and you remember this from 2350, the last remainder becomes your most significant hex character, followed by whatever's above it until you're done, okay? So that's interesting. That means that 176 equals B0 hex, but again, I want 16-bit value. This is positive, so I'm going to sign extend B0 to a 16-bit 2's complement number. Okay, that means, guess what? My answer is 00 B0 base 16. Conversion done. Okay? So positive's easy. When I want to determine what the 2's complement representation of a negative number is, I'm going to calculate the 2's complement of the positive magnitude, or in this case, 88. Well, first of all, 88 equals what in hex? It equals, 16 goes into 88, 5. 5 times 16 is 80 with 8 left over. But again, I want this to be a 16-bit number, so 0058. What I'm going to do is calculate the 2's complement of positive 88. So FF minus 0058. 15 minus 8 is 7. 15 minus 5 is 10, or A. 15 minus 0 is still 15. 15, and I don't want to forget to add 1. My final answer here is going to be FFA8. Okay? Okay, so what do you think? You okay with it? We'll do some more examples of this if we need to. But in the meantime, let's keep going. Let's do some other examples. This time, let's do some calculation based on going the other way. Let's go from 8-bit 2's complement to decimal. So what is the decimal equivalent of the following 8-bit 2's complement values? Again, if it's positive, that means all I'm going to use is expanded notation to tell what this is going to look like. So I've got 5 times 16 to the 1 plus 8 or 10, a or 10 times 16 to the 0. Okay, 5 times 16 is 80. And then 16 to the 1, anything to the 0 power is 1. 10 times 1. So this equals 90 in decimal. Okay? When I am calculating the decimal equivalent of a 2's complement that is a negative, and I can tell that by looking at the leftmost hex character. If it's 0 to 7, it's positive. If it's 8 to E, it's negative. Now, I say that 7 hex, remember, looks like this in binary. So 0 to 7, it means the leftmost bit is going to be 0. 8 looks like this. 8 to F, F looks like this. So the leftmost bit is a 1. So I can still look at that leftmost bit and say if it's a 1, it's negative. If it's a 0, it's positive. And if I convert that to hex, if it's 0 to 7, it's positive, or 8 to F, it's negative. So this is a negative. That means if I, and here guys, listen carefully, if I calculate the 2's complement of a negative value, remember when we calculate the 2's complement of a value, we are negating it. So when I negate a negative value, I should see what the positive representation looks like. So in this case, 8-bit, so here's 2 to the n minus 1, minus my value, E0, F minus 0 is F, F minus E is 1, plus 1, F plus 1 is 16, which is 0, carry my 1 power of 16, or 2, 0. But that's in hex, so what I have to do is convert this to decimal. That's the decimal magnitude. However, since this is negative, I always want to put a minus sign in front. Okay? All right, so a couple of examples. Let's talk quickly about the difference between something we've encountered before, or we encounter it in decimal all the time, but we never necessarily think about it in fixed length, because when we're doing this in our heads or on a calculator, or if we make it big enough on a calculator, we can make it overflow from a sign perspective. But let's do exactly what this says. Let's add the following 16-bit 2's complement values. Notice here, since I've told you both the format and the fixed length, I'm not going to include a 16 subscript or an H after these. Okay? I've already told you what the format is. Therefore, you read them as 16-bit 2's complement values. C plus C, 12 plus 12 is 24. 16 goes into 24 how many times? Well, it goes into there once with 8 left over. Okay? Here, let's do this. C plus C equals 24. 16 goes into 24. Goes in there once with how much left over? 8. 16 goes into 1, 0 with 1 left over. So 1, 8. And that's what we got. We put the 1 here because we're carrying that power of 16 over. Put our 8 down here. 1 plus F, 1 plus F, or 1 plus 15 is 16, which is 1, 0. 1 plus A is 1 plus 10, or B. And then 3 plus 6 is 9. Okay? So, there's our value. Let's look at this and say, what were we expecting our answer to be? Well, the way to think about that is, look first at this value. Is it positive or negative? And you say, oh, that has a 3 as a leading hex character, so it's positive. So I'm adding positive to a positive, which means I should get a positive. But I look over here and say, whoops, I got a negative. So guess what? Signed overflow occurred. Signed overflow occurred. Okay. So I can do the addition, but I didn't get the right answer. When I add two positive values, I expect a positive result. But I didn't get one. I got a negative one. So signed overflow occurred. Let's do another couple of these. Let's do A002. Again, these are 16-bit 2's complement plus 6F01. Okay, just before we get started, we're adding a negative to a positive. When you add a negative to a positive, you will never get sign to overflow. Remember, when you're adding two values of unlike sign, the sign of the result is going to be the same as the sign of whichever value had the larger magnitude. So the answer, when I'm adding two values of unlike sign, can go either way, depending on which of these numbers have a larger magnitude. So I'm never going to get signed overflow when I add values of unlike sign when I'm doing it in 2's complement, some fixed length 2's complement. So we do our addition. I get 3, 0, F. 10 plus 16 is 16, or 1, 0. My answer as a 16-bit 2's complement number is this, which happens to be a positive. Okay? Now, I had a carryout. That doesn't matter. This is a 16-bit value, and this, ladies and gentlemen, is the correct answer. Okay? Remember, that's why we love 2's complement. All right. Let me do one more, just so we kind of get this down. Let's say A002 plus AF01 instead of 6F01. So here I'm adding two negatives. I should get a bigger negative, and in this case I get 3, 0, F. 10 plus 10 is 20. 16 goes into that once with 4 left over. Whoops, I got a positive. So guess what? In this case, signed overflow occurred, which means my answer is incorrect. Now, the reason we bring this up is because later on when we get into the instruction set, there are ways you're going to be able to note whether something like signed overflow or a carryout have occurred. Okay? All right. We're probably, let's see how fast we can go on this next bit here. I want to quickly look at internal storage of numbers. This hopefully is a refresher from 1430 days. Let's say, oh wow, if I want to declare something to be of type int and float. Both of these are going to allocate on an Intel-based processor. Both of these are going to allocate 32 bits. In the case of my integer, oh, let's see if I can do this. It's going to be ugly, guys, I'm sorry. But I just want to draw all 32 bits. Oh, that's not pretty. I'll do that. Okay, believe it or not, that's 32 bits. When I declare an int, that is all magnitude. All magnitude. Okay, when it's a float, it's also 32 bits. But here's the difference. Okay, when I'm dealing with floating point numbers, let's just pick one. Let's say, how about 6.02 times 10 to the 25. I write this out in scientific notation where I've got several different pieces. This happens to be my exponent. This is my base. And this is my mantissa. Okay, so floating point, I'm going to have to, the base is going to be assumed. I'm dealing with binary, so my base is going to have to be 2. I have to be able to store a sign, the mantissa, and the exponent. So what we're going to look at is single IEEE, single precision floating point formula or format. Single precision, wow, floating point format. Okay, so that's what we're going to do with this. Let's keep going on this one and say, okay, how do we even start? Well, let's say we have something kind of simple, like 12.5. Easy thing to do here is let's try to come up with a rubric for how to do this. And guys, what I'm going to tell you is there are 5 steps. They're so important that I'm going to number each one of them. First step is I want to convert this decimal floating point number to binary, its binary equivalent. I'm going to do it in 2 parts. I'm going to deal with the whole number first. This is positive, by the way, so I'll go ahead and just say it's positive. 12 looks like that. Okay? How do I tell what 0.5 is? Well, 12.5, okay? This is the ones place, or 10 to the 0. This is the tens place, or 10 to the 1. This is the tenths place, or 10 to the minus 1. In the same way, this is 2 to the 0. This is 2 to the 1. So the place after it is going to be 2 to the minus 1, which is the same as 1 over 2 to the positive 1, which is 1/2, or 0.5. So guess what? Now, that's reasoning our way through it. Let me show you the quick and simple way. I'm going to take the floating point portion, or the decimal equivalent of 0.5, multiply it by 2. When I do, I get 1.0. I take whatever's to the left of the binary, of the decimal point, and move it right here. I'm left with 0. What I would normally do is say, okay, let's keep going. 2 times 0, however, is going to be 0.0. I can continue to move zeros, but they're trailing zeros, so I don't really need them. So let me just say, when I'm left with a 0, I'm done. Okay? First step, 12.5 decimal equals 1100.1 as a binary floating point number. Second step is we want to put this in normalized scientific notation. So normalized scientific notation means I'm going to, let me change colors just to make this a little bit easier. Oh, let's go to something we haven't done yet. How about green? Okay, I want to move this binary point 1, 2, 3 places to the left. So this is going to become 1.1001, still a binary number, times 2, which is my base, to the 3rd power. So guys, this is my second step. It is probably one of the more critical steps in this conversion, because from this this binary floating point number in normalized scientific notation, I get all parts of the conversion, okay? So let me change color again. So first step, second step, I need, going back, I need somehow in those 32 bits to indicate the sign. So let's just do that next. 3. The sign. This is a positive value. So my 1 sign bit is going to be a 0, base 2. Okay? Now, I'm going to do this next part in several pieces and tell you that in IEEE single precision floating point format, the exponent that is stored in excess 127 format. Wow, that didn't work out well. Let's see if I can do that better. 127, okay? Excess 127. Is the format. So let me explain to you why. The next 8 bits, because in single precision floating point format we've got 32 bits. The first bit is going to be the sign bit. The next 8 bits are going to be the exponent. The remaining 23 bits will be whatever we use for the mantissa. Okay? We're going to use excess 127 because when we are comparing two exponents to tell, is this a positive exponent? If so, how big is it? Is it a negative exponent? If so, how big is it? Remember the difference or the counterintuitiveness of the negative values in 2's complement. When I add 127, that makes everything an unsigned number. It kind of shifts my range all to positive. So a comparison between the exponents becomes very easy to do. So we'll go back to that, but for right now, I go back to step 2 and I say, okay, my exponent was 3, so 3 plus 127 is the same. Here I'm going to do a little bit of trickery with math. This is the same as 2 plus 128. Why did I do that? Because that happens to be a power of 2. That happens to be 2 to the 7th. So I'll be able to tell immediately what the exponent stored is going to look like. Okay? So that's what I've got so far. Let's see if I can recoup some of this. Let's say 0.1 1.1001 times 2 to the 3rd. We knew that my exponent stored was 1,000,000, what was it? 3, 2, or 128 plus 2. Okay, 3 plus 127 is 130. 128 plus 2 is also 130. So my exponent stored looks like this. Sign, let me just write this. I'm trying to give myself a little bit more room. The only thing left that we have to worry about is the mantissa. Okay, so this was 3, 4, 5. Mantissa. I've got 23 bits. So I can store 23 bits. All right, I need your thinking caps to go on, because here we need to talk a little bit about this. I can, if I store this portion of the value, I can do that, but I'm going to be taking 5 of my 23 bits to do it. Not a problem, because this is a relatively small value in terms of the number of binary places I need. But what if this is something that is a transcendental number or has an infinitely repeating binary place? What if I had something like 1 point, oh, writing is hard, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Whoops, what happened there? Let's go back. Darn, it erased everything for us. Okay, that's okay. Let's just talk about the mantissa. In my previous example, I had, right up here, I had something that had a total of 1.10 dot 011, say, and I had 27 bits, but I only have 23 bits to store it. So that means I'm going to have to lose 4 of these bits. So I can either truncate the last 4, or, and this is kind of ingenious, okay? I sit and I think to myself, you know, there's only one case when I'm dealing with binary floating point numbers that in normalized scientific notation I'm not going to have a 1 to the left of the binary point. Remember, this was 1100.1 or 1.001 times 2 to the 3. This is normalized scientific notation, and I have a 1 to the left of the binary point. For every binary floating point number, this will be the case except for 0. 0 doesn't work with this, okay? It has its own representation, and I'll talk a little bit about that, but for now, let's hold off on it. We won't actually, in fact, I won't answer that question actually until we get to chapter 9. So let's just finish this. This means, since I always have a 1 to the left of the binary point unless the value is 0, means I can save one of my 23 bits and just store what is to the right of the binary point. This is called hidden bit notation. Okay? Which means I'm going to take just those values that are to the right of the binary point and store those. So 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, whoops, 0, 0, 0, 0. This is why I hate binary, by the way, okay? There it is. Now, guys, we're going to put everything together. This was my sign bit is the leftmost bit. It was a 0. My stored exponent was 128 plus 2, or 130, which looks like this. 128 plus 2. And then the remaining 23 bits are my mantissa, which looks like this. 0, 0, 0, 0, dot, dot, dot. Don't do this on your homework. I'm running out of space, okay? So I'm going to go through here and say, okay, let's break this up into groups of 4 bits so that I can show this 32-bit binary number as a hex value. 0100 is 4. This is 2. This is also 4. This is 8. That's 0, and the rest of these are 0. So guess what? 12.5 in decimal will look like this in the machine in IEEE single precision floating point format. Guys, those are the rules. When we get to class, we'll do positives and negatives, but for now, that's it.